Hello everyone, I'm Giovanni Pelliccioli and I will talk about next to leading order corrections to off-shell TTW production at the LHC. What are we talking about? At the LHC, we mean proton-proton collisions at high energy, order 13 TeV in the run 2. And TTW at the LHC means a quark-induced process. Here I show, for example, one leading order diagram for on-shell top, anti-top, W plus production. This picture is definitely not enough in order to be realistic because these particles are heavy and unstable. So therefore we need to model their decays. And these are the typical decay products. So charged leptons, neutrinos, and B quarks. This is still not enough, even at the perturbation theory level, because of course, this is just leading order, and here I obviously show just one sample diagram. Therefore, we need to go beyond in order to be more accurate and include also radiative corrections to the leading order. So next to leading order and so on and so forth. Next to leading order is automated, both for QCD corrections and for electro-weak corrections, but still features challenges in the numerical integration, for example. But this is still not what is measured at the LHC. In order to be much more realistic, we need to go beyond the perturbative description, and we need somehow to sum a certain class of dominant higher order contributions via a sort of resummation, which is achieved by the so-called Parton shower method. This is also automated. It is an approximation, of course, but gives results which are much closer to what is actually measured in the detectors. And what is measured in the end is the Parton showered result and after hadronization and multi-parton scattering modeling. So the non-perturbative description of the process after Parton shower. This is also automated, and this is what we see in the detectors, right? So hadrons and rest leptons. What I will focus on in this talk is radiative corrections to the off-shell process of TTW production at next to leading order electroweak and QCD. This features quite hard numerical integration because of the high multiplicity final state we will consider, due to a lot of contributions which participate in the computation for this process. But what I want to stress is that even this is just a perturbative description, the state of the art, I would say perturbative description. It features already interesting phenomenology to study in order to address the actual experimental analysis in this process. Why TTW? TTW at the LHC is one of the heaviest signatures and also a rather rare process. It's optimal for studying the coupling in or beyond the standard model between top quarks and weak bosons. And in particular, in the multi-lepton final state, it can embed several new physics effects due to the fact that when one has same sign leptons, for example, SUSY particles can be around, so beyond the standard model effects can be around in the game. It's important also for studying charge asymmetries because it is a quark-induced process, and the symmetric gluon-gluon partonic channel just opens up at next to leading order QCD. So it enhances the sensitivity to the top quark charge asymmetry. And it's also an important background to associated production of top quarks and the Higgs boson. TTW has been measured with the latest run 2 data of the LHC at 13 TeV by Atlas and CMS collaborations, but a tension between data and standard model theory predictions was found both in direct and in TTH measurement. This means that we definitely need an improved theory modeling for this process. This is the process that we study. So this is the final state: 2 B quarks, 3 charged leptons, and 3 neutrinos. And we study it at NLO accuracy. Already a leading order, this process, which embeds the TTW resonance structures, received contribution from two different perturbative orders, leading order QCD and leading order electroweak. In principle, also the interference among two sets of leading order diagrams contributes, but this is identically zero due to color structure. So I want to stress that not all of the diagrams in the given perturbative order embed the resonant TW structures. This diagram, for example, embeds the resonant structure of W top anti-top, but this one doesn't. And this holds also for the purely electroweak diagrams. Next to leading order is definitely more involved, and we computed the NLO 1, 2, and 3 corrections to TTW production in the off-shell case. I want to stress that when dealing with NLO corrections, one needs to sum over real and virtual corrections, because just the sum of the two sets of contribution is free of singularities of infrared origin, both in the QCD sector and in the QED sector. So when one computes the NLO2 corrections, for example, one needs to sum over all these classes of contribution, which is definitely not straightforward because one needs to compute difficult loop integrals up to 10-point functions need to be reduced and evaluated. And from the real side, one has also to sum over different contributions. And in particular, one needs to subtract IR singularities in a numerical way in 4 dimensions, because 4 dimension is where a Monte Carlo lives. And in particular, for this process, we have to integrate with Monte Carlo methods a 2-to-9 process, which is definitely not straightforward due to a very large phase space measure. We computed TTW production in the off-shell case, considering the previously shown final state in a realistic setup. So to say as close as possible to the kinematic selections that Atlas made in their latest measurement of TTW. This is a rare process because the cross-section also at next to leading order is order 0.26 femtobars. So at the LHC in run 2 data, there should be around 35 events, which need to be extracted from all the rest of the backgrounds and so on and so forth. So this is not just these 35 events and nothing else. The leading order QCD is already big, so the NLO corrections are all of the order of a few %, but they're definitely sizable. NLO 1 corrections for this scale choice amount at 7%, but they strongly depend on this central scale choice. NLO 2 corrections are negative, order -5–6% as expected, and rather scale independent. NLO 3 corrections are much larger than the corresponding leading order and larger than NLO 2, even though by power counting of perturbative couplings, one would expect the other way around. Theory uncertainties reduction from leading order to next to leading order are dominated by the NLO 1 behavior. Total cross-section are not the end of the story, because one needs to see whether the NLO corrections also distort the shape of this differential cross-section in a certain observable. And I want to say that all of the 3 NLO corrections distort significantly some distribution shapes. And for example, here, I show the invariant mass of the 3-charge lepton system, which is definitely measurable at the HC. And you can see in this relative plot with respect to a leading order QCD that all of the 3 curves, NLO 3, NLO 2, and NLO 1, distort significantly the shape of leading order. I hope I convinced you that the perturbative description of LHC processes is not the end of the story, and is that the first step towards a realistic prediction. NLO QCD and electroweak corrections feature several challenges, both from the point of view of Monte Carlo integration and from the point of view of the decay modeling of a resonance structure, for example. TTW is a rather rare signature and a heavy signature, which is, however, very interesting both to probe the standard model and also for new physics searches purposes. We have computed NLO QCD and electroweak corrections, including all off-shell effects, so spin correlations and resonant effects. And we found out that all of the relevant NLO corrections, so NLO QCD, but also NLO electroweak corrections of NLO2 and NLO3 type, are definitely needed to provide realistic NLO predictions for this process. Thanks for your attention.